This video provides background material for the Nodal Pricing course. Dispatch is the process of matching generation to meet demand in real time, and this is undertaken by the system operator, a division of Transpower, at least every 5 minutes. The dispatch objective is spelled out in Part 13 of the code and is to meet demand at minimum cost to purchasers, subject to security and other constraints. The other relevant information here is that a lot of the constraints are covered by the system operator's security policies. Now, when we talk about the cost of dispatch, we're talking about the cost of providing consumers with electrical energy based on offers for generation and reserve capacity. This is not to be confused with generators' costs, such as fuel costs. The costs we're talking about in nodal pricing are entirely driven by the offer prices on generation and reserve offers. We often speak of marginal cost, which is simply the change in cost due to a small change in supply, for example 1 megawatt hour. Sometimes you'll hear the term incremental, which is also used to mean marginal in some contexts. Now, what do those energy offers look like? Generators can submit up to 5 bands in each offer for a unit or a station, but let's have a look at this example. The offers range from 1 cent per megawatt hour up to $95 per megawatt hour. For example, let's imagine the generator is dispatched at 350 megawatts, which is 20 megawatts into its 4th offer band. Now that means that it has an implicit contract with the clearing manager to be paid at least $65 per megawatt hour for all of its generation. Now, if the spot price at its node is $65 per megawatt hour, then its revenue is the area of the orange rectangle, divided by 2 because of the half-hourly trading periods. So in this example, the trading period revenue would be 1 half hour times $65 times 350 megawatts, or $11,375. The fact that the generator has offered it lower than $65 per megawatt hour, and those lower priced offer bands have been dispatched, is irrelevant to what the generator actually gets paid. Now, after talking about generator offers, we need to cover off demand bids and also the issue of where forecasts are used. Now, certain spot purchasers must submit bids for power if they buy at what are known as non-conforming nodes. These are nodes which are deemed by Transpower to be difficult to forecast ahead of time effectively in terms of their demand. Typically these are nodes with large industrials at them, so Edgecombe, Glenbrook for New Zealand Steel, Carrowell, Norske Skog, Kinleith, Carter Holt Harvey, and so on and so on. The bids are called nominated bids, and they're required for all of the retailers and other spot purchasers at those non-conforming GXPs. Retailers can also submit difference bids, which are there to signal intention to reduce load at a price. And finally, forecasts of demand are made by the system operator, and they're used at conforming nodes for the purposes of actual dispatch and to produce forecasts of prices and dispatch ahead of the actual trading period. The nominated bids submitted at non-conforming GXPs are used only for producing forecasts of prices and dispatch. They are not used to actual dispatch, and they're not used for calculating the final prices actually used for settlement. They can contain up to 10 bands for each purchaser at each non-conforming node, and those purchasers must use reasonable endeavours to predict demands at each price in the bid. The bids have to be submitted at least 71 trading periods prior to the trading period, but they can roll over automatically. Gate closure applies just as it does for generator offers, except where there's a bona fide physical reason, for example unplanned outage of plant, or there's a grid emergency. And in any case, nominated bids must be modified if the spot purchaser expects their load to vary by 20 megawatts or 20%, whichever is smaller, from their current bid, but there is an exception for any expected variation under 5 megawatts. And all rebids within gate closure period must be reported to the Electricity Authority. And when we talk about nodal dispatch and pricing, we're really talking about the SPD model. SPD stands for Scheduling, Pricing and Dispatch, and it's a very large linear programming model used to calculate the optimum dispatch and to calculate nodal prices in what's known as market schedules. But there's some loose ends that we have to cover off, and this is because real-time dispatch is subject to factors not well modelled in a linear model such as SPD. For example, very short-term variability of demand or generation, for example, intermittent generation, that's wind and increasingly solar, or very fast changes in demand, as sometimes you might find on a large industrial site. Secondly, we have the risk of failures. That could be either a generator or it could be a transmission line in the grid. So to cover off these loose ends, we have the frequency keeping service. We must provide instantaneous reserves. And there's the simultaneous feasibility test, or SFT, which we'll talk about when we get on to constraints on the grid. But let's look at frequency keeping first. There has to be at least one frequency keeping station, and that's there to make sure that the system frequency is maintained at 50 Hz. If the frequency moves too far from 50 Hz, then we potentially have some major problems. So the frequency keeping station's role is to maintain frequency in the band 49.8 Hz to 50.2 Hz. Now, it's possible to have more than one frequency keeper working together in an island, but each frequency keeper has to be able to move plus or minus 15 megawatts from its dispatched set point to maintain system frequency. Since 2013, the HVDC link has been fully upgraded, and it normally now operates in frequency keeping control mode, known as FKC. That means that frequency keeping duty can be shared across the HVDC link. So you can literally have the frequency keeping station in one island, which is keeping frequency for that island, and with FKC mode enabled in the other island as well. So in this mode, the HVDC link modulates to keep the frequency the same in both islands. FKC mode may be turned off occasionally, for example if there are certain outages, or perhaps when HVDC transfers are very high. And in those instances, you would need at least one frequency keeping station in each island. There's quite a lot of terminology associated with the reserves, and what we'll see in the course itself is that reserves adds a lot of complexity to dispatch and pricing. So key to all of this is the concept of an outage, which is simply an event where a generator or a line in the grid is suddenly unavailable. This is also known as a trip or a contingency. There's different classes of reserve. FIR stands for Fast Instantaneous Reserves, used to be called 6-second reserves, and SIR is Sustained Instantaneous Reserves, previously called 60-second reserves. If you look in the code, you'll find a definition for contingent event, which is literally an event where resources are able to be economically provided without disconnecting demand. What this typically refers to is either the loss of one transmission line, or for our purposes in the Nodal Pricing course, it's the loss of a generator or one half of the HVDC link. The other definition you'll find is the extended contingent event, and this is where we can only keep things operating by disconnecting demand. And the key event here that's considered is the loss of both poles of the HVDC link, when the HVDC link is sending a lot of power into an island without disconnecting demand. As well as two classes of reserves, there's also different types of reserves. The first we'll look at is TWD, which stands for Tail Water Depressed. It only comes from hydros, and only when the hydro unit is not actually generating electricity. And the generator can be run as a motor from the grid. So in the diagram, we've got a dam in cross section with a storage lake behind it and a penstock. And at the bottom of the penstock are wicket gates, which are closed. So if we feed power into the generator, we can get it spinning in synchronization with the grid. If this generation is suddenly required, in other words, if the frequency starts to fall below 49.8 Hz, the gates can open, water will flow down the penstock through the turbine, down the draft tube and out into the river, and the generator will start injecting power onto the grid. That can happen very quickly because the generator was sitting there synchronized with the grid. The second type of reserves, which is very important, is known as PLSR, which stands for Partly Loaded Spinning Reserve. And this is provided when a generator is running at less than their full offered output. So a generator might be running at 100 megawatts, for example, even though they've offered in 200 megawatts. So there could be up to 100 megawatts of reserve provided from that generator. That's capacity which isn't used, but could be used if there's an outage. Now that's typically provided by hydro or thermal generators, but it can in principle be provided, for example, by wind farms if they have the control system capability to run below their maximum output for any given wind speed. In New Zealand, there are no wind farms that provide this currently, but it does happen overseas. And finally, we have interruptible load reserve, ILR. This is offered by purchasers, and they connect certain large loads through a frequency-sensitive relay, which is typically set to trip. In other words, disconnect the load when the frequency falls below 49.2 Hz. Now, although AUFLS, which stands for Automatic Under-Frequency Load Shedding, is not actually a type of reserve, we'll mention it here because it is relevant. This is required of lines companies and some large consumers in 2 blocks of 16% of load in each block. If the frequency falls far enough, then AUFLS will disconnect. Now in the North Island, the block 1 sheds at 47.8 Hz and block 2 at 47.5 Hz, or when the frequency remains below 47.8 Hz for greater than 15 seconds. Hydro generators tend to be more tolerant of frequency changes. So in the South Island, block 1 sheds at a lower value, 47.5 Hz, and block 2 at 46.5 Hz. Now, AUFLS comes under a new regime called Extended Reserves, which is currently under development. In the future, this will allow AUFLS effectively to be procured in a market mechanism rather than being mandated on lines companies. Now, I want to have a look at what actually happens after an outage. So an outage has occurred, time t equals 0. We'd like the system frequency to be at 50 Hz, but because we've lost some generation, for example, frequency is now starting to fall quite rapidly. Now, the rate of decay is influenced by a number of things, particularly the amount of load and generation. So in winter, the frequency will fall slower than it will on a hot summer night when the load is much lower. And this is because there's more inertia in the system when the load and the generation are higher. Big generators are big, heavy machines. They're spinning, and because of that, they store a lot of energy. They have a lot of inertia. And by virtue of all of that inertia connected to the system, there's more energy available to maintain frequency for longer. If the frequency were to fall below certain values for even a couple of seconds, then that could lead to what's known as a cascade failure in the extreme case. A cascade failure means that things start to turn off in sequence because the frequency keeps falling, and eventually all the lights everywhere turn out. But frequency keeping and the reserve regime are there to prevent that happening. So what will happen is that at 49.2 Hz, ILR will trip off, and even by then, fast instantaneous reserves will have been activated, and combined with the ILR will stop the frequency decay. Then SIR, which is coming in through this period, will pull the frequency back up to 50 Hz. Now in the code there are certain requirements regarding the frequency fall after an outage. So for example, more FIR is required if the minimum frequency after an outage drops below 48 Hz for a contingent event, or for an extended contingent event, 45 Hz in the South Island and 47 Hz in the North Island. We can see this in action looking at recent under-frequency events. For example, E3P tripped off in May 2016. It's a loss of between 300 and 400 megawatts, and the frequency dipped down to below 49.2 Hz for a few seconds before rebounding, and it actually went over 50.2 Hz as it recovered before the frequency keepers brought it back into the plus or minus 0.2 Hz range. If we go back to 2012, we can see an even more extreme case of this overshoot when 165 megawatts of interruptible load reserve, a whole pot line at the TY smelter, tripped off after an under-frequency event initially occurred. The frequency in the South Island overshot 51 Hz before the frequency keepers brought it back under control. Now, in order to be scheduled or dispatched for reserves, you have to submit offers for reserves, in the same way as generators submit offers in order to be dispatched. Now, in the case of a generator, you might be able to provide FIR and SIR, or both at the same time. So you have to specify in your offers whether your reserve is FIR or SIR, and there's also a different offer form for each of PLSR, TWD and ILR. ILR can be offered as FIR or SIR, and those can be provided at the same time. There can be up to 3 bands in each reserve offer. You need to specify the class, FIR or SIR, and what type of reserve it is. Now, just to round this section off, if you are actually dispatched for reserves or for frequency keeping, you will be paid for that. Reserve providers are funded by generators and the grid owner. So generators and the HVDC link, which is owned by Transpower, create the risk. There is a de minimis, as it's known, of 60 megawatts. So when the HVDC link in a trading period is running over 60 megawatts, or when a generator is running over 60 megawatts, then those parties will have to contribute to the reserves funds, which are then paid out to reserve providers. The only other thing to add here is that there is a penalty for any plant that's unlucky enough to cause an under-frequency event due to an unscheduled outage, and this applies to both generation and the HVDC link, and currently that's $1,250 per megawatt for each event. The total payments to frequency keepers are totaled up and allocated out to spot purchasers pro rata on their demand in each trading period. Now, we're primarily talking about the SPD model, but there's another model called RMT, which stands for Reserve Management Tool. And recall that SPD is a linear model, and as a result of that and some technical factors, it tends to overestimate the amount of FIR actually required. So RMT is run alongside the SPD model. It's a dynamic, non-linear model of the system frequency, contains a lot more detail about generator response and inertia, etc., than does the SPD model, and it produces parameters which are fed into SPD called risk offsets. So SPD does contingent events, single generator risk, and one pole in the HVDC link, and the amount of FIR that it calculates to cover that is effectively compared to the same numbers coming out of RMT, which considers contingent event and extended contingent event and has that much more detailed modelling. And that comparison is used to produce the risk offsets, which are actually used in the SPD model. Now, risk offsets are actually very simple. It's simply the reserve scheduled by SPD minus the reserve scheduled by RMT. So if RMT calculates less reserve than SPD, then the risk offset's greater than zero, and vice versa. Now, generally risk offsets are greater than zero, and this is because of net free reserve, NFR, calculated by the RMT model. Now, NFR arises for a couple of reasons. One is that all of the large generators connected to the grid control their output based on frequency. The control systems are known as governors. So if a generator is dispatched for reserves, that's fine, its governor will respond to low frequency. But even if it's not dispatched for reserves, then the governor will still respond to frequency. Hence, there's some free reserve available. And the other factor is that inertia that we've already covered. Now, there's been a recent change in the way that reserve is dispatched. We now have a national market. Prior to November 2016, reserves were dispatched separately at each island. Now reserves are dispatched across the country, and this is possible because of the upgraded DC link and the frequency control mode, which we've already mentioned. From the 17th of November 2016, the HVDC link has effectively been able to provide up to 220 megawatts of shared reserves between the islands. Now, just taking a relatively random winter week, this one's first week in July 2014, we're looking at the South Island risk offsets. FIR in the orange and in the grey are the SIR risk offsets. Now, the SIR risk offsets on this particular day were zero across the day, but the FIR risk offsets exceeded 110 megawatts. So these risk offsets are very significant and vastly reduce the amount of reserves that are actually required to be dispatched. If we look at the North Island on the same day, we can see an even bigger effect with the risk offsets for FIR approaching 200 megawatts during the day. Interestingly, on this day, the SIR risk offsets were actually slightly negative all day. Now, what does that mean? It means that more reserve is required than is actually dispatched by the SPD model. So just to sum up here, FIR risk offsets are normally positive, which means that SPD is dispatching less FIR than it would otherwise. SIR risk offsets are typically zero. Occasionally, they also go slightly negative. Now, finally, we'll just briefly mention some terminology that we'll use during the day. So the summation sign, sigma, for some variable x over g is simply equal to all the instances of that variable. We won't be using that summation very often, really in just a couple of slides. We'll use S at n for the nodal spot price at node n in dollars per megawatt hour, and Pn as the power flowing in line n on the grid. Squiggly equals means approximately equal to. And here's a term that you need to be familiar with, infeasibility. This is when SPD cannot find a workable solution to the problem of minimising the cost to purchasers. This typically means that there's some constraint on the dispatch which simply cannot be satisfied. Now, what happens in this case is that there are phantom generators and reserve providers within the SPD model which are dispatched during an infeasibility. Now these are set at very high prices, so when an infeasibility occurs, the signal of this is prices coming out at around $500,000 per megawatt hour. Now those prices aren't published and used for final settlement. They're a signal that the model solution needs to be reworked so that a feasible dispatch and pricing solution can be found.